wrote about a book on that, or Springer, and philosophy of mathematics in general. And you have the floor.
Okay, thank you. Well, thank you also for inviting me to come here. Unfortunately, I'm not as polished as the other speakers who can speak impromptu and stay within the time and so on. So I'm going to have to read my paper. I'm very sorry about that. Otherwise, I will either speak for too long, or I will speak for too little, or I'll miss something out, or I'll say the words in the wrong order. So, all right, so I want to begin. This is just the order of go. I want to begin by the notion of individuating mathematical theories. So I'm going to start talking about mathematics, and then I'll move to chemistry afterwards. In mathematics, theories are rigidly and precisely delineated or individuated. That is, we can precisely give their identity conditions, conditions that allow us to tell if two presentations of theories are in fact equivalent, or if two presentations of theories are distinct. So mathematical theories can be individuated in terms of axioms and a syntax, as when we talk about Zermelo-Fraenkel set theory or second-order piano arithmetic. We can also individuate mathematical theories in terms of the objects being studied, such as group theory or ring theory. We also individuate mathematical theories in terms of the operations, such as when we do calculus, matrix algebra, the lambda calculus. And lastly, there might be others as well, I just brought these up. We might individuate theories in terms of the context that sets the parameters on what we may or may not do, for example, Euclidean geometry or topology. We might even individuate the same theory in several ways, right? So these are not preclusive of each other. So we may think of geometry as the study of the relationships between points, lines, and planes. So in terms of these objects of study, different geometries then study these objects under different circumstances or different metaphysical or meta-mathematical assumptions about symmetry, straightness, orthogonality, or parallelism. How one characterizes a theory in mathematics is partly a matter of temperament, or how one thinks, and partly a matter of what it is that one likes or finds familiar in mathematics. And what one finds familiar is partly a matter of the particular mathematical education one received, and partly a matter of how much one enjoyed the parts of the particular education. So some people really take to certain areas of mathematics, other people just don't take to others. We have all heard the stories of people having difficult or revelatory experiences in mathematical education, when nothing makes sense, or when it all falls into place. And we have all witnessed curriculum changes, right, which try to respond to this and try to help students to have the relevatory experiences and not so much the I'm completely lost experiences. In many ways, these different approaches and educational paths are irrelevant to the subject matter of mathematics, since the community of mathematicians can come to agree on precise definitions, although this might take some time. And the precision is only ever up to our conceptual sensitivities. So precision might be made more precise later. The subjectivity of the experience of the mathematical concepts only make a difference in terms of who develops which mathematics when. In other words, it makes a difference to the history of mathematics. And this can be conceptually separated from the body of knowledge such as it is at any one time. There is a path that led us up to our present collective understanding, and this is different from what it is that we understand of the whole, insofar as there is one. That is the whole of mathematics. The first has to do with historical explanation. The second has to do with what we know and where we can go next. What are the proximate, that is the closest, undeveloped concepts in mathematics that are available to us? Of course, this is not to say that the history of mathematics should not be studied. On the contrary, the history is very rich and affords us a perspective from which we are accorded the freedom to revisit our mathematical concepts. For in studying history, we learn that it takes time for mathematical concepts to gel. Right? There are controversies in the history that we don't know about. So sometimes when we're presented with a mathematical textbook, it's all given to us as though it's given by God, right? This is how it works, and there's no explanation about how people struggle to get there. When we study the history, we learn about those struggles. And those struggles tell us about how we should deal with the struggles now. That there are concepts that it allows us to question the concepts that we think are gelled. Maybe they're not as gelled as we think they are. Even a formal language holds ambiguities, sensitive to at least context, the surrounding implicit definitions. For example, the notion of set has a different implicit definition depending on the particular set theory one is studying. There's an informal idea, what Byers calls a proto concept. I quite like this vocabulary, right? So it's a proto concept that you're after when you develop a formal representation of that proto concept. And we want to separate the proto concept from the formal representation. Then how loyal the formal representation is to the proto concept, or whether there is anything very precise to be loyal to, or to what extent we know the concept better after formal representation, is a philosophical matter. The how loyal question arises from a Platonist type perspective, where we think that the proto concept is grasped through mathematical intuition. The whether question arises from a formalist perspective, and the knowledge question arises from a constructivist perspective, just roughly speaking. Right? And I'm not wedded to any of this. So now we move on to the next part, inconsistency in mathematics. There are two types of, and do interrupt if you want clarificatory things, and if it's deep question, I'll hold it until the end. There are two types of inconsistency that mathematicians face. One is inconsistency internal to a proposed mathematical theory. The other one is an inconsistency between theories. We've heard a lot about these. The first can lead to one, abandoning the theory. So again, it depends on how we individuate that theory. So if it's individuated by axioms plus a syntax, you might change an axiom, then we suddenly have a new theory, right? So we abandon the first one, strictly speaking. We didn't abandon all of it, but we abandoned the theory, and we now have a new theory just in virtue of having changed one axiom. Right? Again, this depends on how we individuate these theories. So the first can lead to abandoning the theory, or to theory revision, where so if we have a different conception of how we individuate theories, you might say, well, we're going to revise how we think of the notion of set, for example. The last and the third one is adoption of a paraconsistent underlying logic. And the last option is rarely chosen, but all three belong to a coherent mathematical practice. Yeah.
Just a clarificatory question. Is there some notion of theory which you have in mind here, like some sets of sentences or sets of axioms?
No, I have all those different ones at the beginning.
Okay. So any one of those.
And so different ones will answer in different ways.
Okay.
Right. So whether you think of something as a theory revision as opposed to an abandonment of theory will depend on which particular conception of theory you have. So I want to keep all of those open. So in the practice of mathematics, I observe that people have different ways of, if they say I'm a geometer, then I say, what do you mean by that? And I say, well, I am studying the relationship between points, lines, and planes from different points of view because I study different geometries. So then I'm not going to be looking so much in terms of axioms. It doesn't make sense.
Okay.
So inconsistency between theories, again, so how we individuate the theories is sensitive, is dealt with by one, monism, abandoning one of the each separately consistent and paraconsistent theories, usually on grounds of intuition about the ultimate and single truth of the matter in mathematics, so some sort of deep conviction, or in what we can know about mathematics if you're more constructivist. By careful cordoning off of formal theories from one another and then moving to the meta level to compare theories, this is a type of moderate pluralism. Well, there are many, anybody who's seen my book knows that there are many different ways of thinking about pluralism and different facets of pluralism and also different degrees of pluralism. But for the purpose of this talk, I'll just talk about this moderate pluralism, or by pluralism which adopts a paraconsistent device or underlying logic at the meta level of the theories in question. The choice between these options is informed by deep metaphysical intuitions such as essentialism, pragmatism, skepticism, anti-realism, or quietism, etc. So now let's talk about inconsistencies within a theory. Yeah.
On the first type of inconsistencies, you have number 3, adoption of a random system in underlying logic.
Yeah.
It has to be so, or is in general change of logic or something?
Well, if there's an inconsistency in the theory, unless you're trivial tolerant.
No. I was thinking in the case of calculus. Some people might change to intuitionistic logic and
Okay, then I would call that theory revision.
Okay.
But because we're dealing with the inconsistency.
Okay.
So moving to an intuitionist version of calculus is not dealing with an inconsistency in calculus. It's maybe dealing with an inconsistency in application or an unneeded part of the theory. I'm not wedded to these.
Okay.
We can. I will accept modifications on this. It's just this was very rough. All right. So inconsistencies now within a theory. And then we talked about this a little bit before, so I'll do it fairly quickly. Constructivists define inconsistency as a primitive entity symbolized by bottom. So I couldn't work out how to do bottom on the computer. So it's basically a big upside down T. In other formal systems, it takes the form of a definition, something like the formula or term is inconsistent or contradictory, if and only if it yields the equation 0 equals 1 or 1 equals 2 or whatever other small arithmetical idea that we think is false. In some logical systems, it's defined as holding between objects, so A doesn't equal A, and in others between propositions, so not P and P. Inconsistency defined in these ways and in these formal systems is the same as the notion of contradiction, right? Logical contradiction. There might be others as well. Right? I'm not proposing a full catalog. Whether we spot these is sensitive to the precision of the language and definitions within a theory. There are famous examples. One is Cantor's paradox, the other is set theoretic paradoxes, and the other set theoretic paradoxes. Another is Frege's logical theory. There are other famous ones, and probably very many of them that are not so famous, since they never made it to print. Right? People were working out a theory, and they found out it was inconsistent, it didn't work, and they just never bothered to publish it. So there's probably lots of these trials that never really made it. So consider the set theoretic paradoxes. So we had a discussion in the earlier talk a little bit about the set theoretic paradoxes, whether they really spurred the development of set theory or whether there are other motivations. But the Russell story tells us, right, that the community of mathematicians was very alarmed by the set theoretic paradoxes. And the mathematicians made more precise definitions of how to construct sets and hoped to avoid paradox and inconsistency. The best classical mathematicians could do eventually to be certain of consistency was to make equiconsistency proofs, showing that if one formal representation of set theory is consistent, then so is another. This is far from the certainty of proof of consistency within a theory. And it is, of course, Gödel who showed us that we could not generate a proof of consistency within a theory of a certain minimal complexity. Constructivists of the philosophical stripe, as opposed to set theorists who so-called construct sets. So there's a little bit of ambiguity in the language. So set theorists will call themselves constructivists in virtue of the fact that they construct sets, but philosophical constructivists have a philosophical motivation. They actually don't accept a lot of what the set theorist do. So they don't accept the general power set and things like that. They have a different approach. They guarantee consistency by beginning only with formulas that they know and deriving through knowledge-preserving rules further immediate known formulas. The first are immediate, the ones that they know are immediate. That is, there is nothing more to say to justify them. The second are mediate, in the sense of mediated. That is, they take mediation or manipulation through a rule to get to them. Personally, I am not, at the moment, convinced by philosophical constructivism. How philosophical constructivists know anything in the first place, or why they think that they know anything at all, is something I do not know, no pun intended. For me, knowledge comes in degrees. There are not things known and things unknown. There are just things known better than before, or they're forgotten, or one person maybe knows something better than someone else. In a less than sober moment, a philosophical constructivist might concede and say that insofar as, say, A and A, where A is a variable over well-formed formulas, is known, and insofar as and elimination is a knowledge-preserving rule, then if a particular instance of A and A is known, then A can also be known. Right? Once we've made all of this explicit, right? So I said insofar as, right? And I said so the qualifier insofar as qualifies as I just know these things, right? It's insofar as I know this, if I know this. Once we make all of this explicit, it's less obvious that we can claim to know anything. The Platonist and the constructivist responses to correspond to 1, theory abandonment, and 2, theory revision in the introduction of this section. And, whoops, that's right. Right, so yeah, so the Platonists and the constructivists correspond to 1, theory abandonment, and 2, theory revision in this. The third response is to use the sense of alarm and not to shy away from the paradox, but to allow it. The paraconsistent strategy or response is to change the logical rules of inference or deduction at the object level within the theory, such that ex contradictione quod libet is not valid. This strategy amounts to the recognition that we can reason rigorously about and with paradox. This is now let me just see if I'll put okay, good. This is a type of theory revision, but it takes place at a deeper level, at that of the underlying logic. It might not be explicit in the presentation of the theory. That is why the presentation of a theory, discussed in the beginning of the paper, is so important for this discussion. There are several ways of doing this, each motivated by different philosophical or aesthetic considerations. What they together show is that it is paraconsistently possible to formally represent rigorous reasoning under circumstances of formally represented inconsistency, that is, contradiction. Since we do sometimes reason in a way that seems to be rigorous, in the sense of admitting recognizable correction, in the face of inconsistency. Not just by putting the inconsistency in scare quotes, so naming it and not using it, or sort of bracketing it, but rather reasoning directly from the inconsistency in a perfectly understandable manner, understandable not by those who are thoroughly trained in classical logic, by the way. And it makes paraconsistent sense that we should be able to represent that reasoning, since representing rigorous reasoning is what logicians have learned to do very well over the last century. These were the more coherent and practiced responses of mathematicians when faced with inconsistencies within a theory. What of inconsistencies between theories? So again, now we're talking about individuating theories in different ways. Inconsistency between theories is not the same as contradiction within a theory. Theories are known to be inconsistent with each other, just in case a pair of theorems, I'm just giving this definition, a pair of theorems or axioms of the theories are written in the same language, and one can derive a contradiction from the pair. We wrote in the first section that there are different ways of individuating theories in mathematics. If we individuate theories by the objects being studied, then inconsistency will consist either in 1, an entity being absent from one theory but present in another. This is expressed at the meta level. So the inconsistency is there exists an entity in A, in theory A, there exists an entity A in theory A, and there does not exist an entity A in theory B. Or 2, saying contradictory things about an object supposed to be the same object in both theories. Or by 3, being able to say certain things about the object in one theory but not in the other because of language restrictions. For example, of 1, the square root of 2 is absent from piano arithmetic but not from analysis. 2, an example of 2. The shortest distance between 2 points is a straight line on a Euclidean plane is true in Euclidean geometry but false when doing geometry on a Euclidean sphere. An example of 3 is 8 minus 10 equals negative 2 is not a statement in a formal language where there are no negative numbers. None of these inconsistencies is a problem for the working mathematician. These are standard meta-theoretical statements, and they are plainly true or false and not both. It can be a problem for the Platonist or realist philosopher who thinks that there's one absolute truth of the matter concerning any object in mathematics, and there's one class of such objects. Thus, it is exactly the same number 8 that appears in the natural numbers and in the integers. So sometimes philosophers speak in this way, it's the same number 8. So the natural numbers are incomplete, and at the meta level, we might even write falsehoods about the entities, such as there is no negative counterpart to the number, no negative counterpart to the number 8. For such philosophers, so these sort of realist one-ontology philosophers, it then becomes very important to work out what is the ultimate class of mathematical entities and how we find out the truths about those entities. There are no longer many such naive Platonists at the forefront of philosophical or mathematical inquiry. Those who held such convictions in the past have had them replaced by more sophisticated ones, such as we see in Balaguer's plenitudinous Platonism. Regardless, such inconsistencies do not disturb mathematical practice. Why not? The practice of mathematics is not disturbed since mathematicians are pretty good at knowing in what context or what theory they happen to be working. Problems can arise when they draw on results or resources A or D. Where's D? D's there, yes. Axioms, theories, or lemmas, or when they draw on results or resources such as different entities, or they deploy operations from other theories. That's an example of C. Sometimes when we do this, strictly speaking, modular our way of individuating theories in mathematics, we are writing or speaking in a new theory. Quite often this is okay, since there is some affinity between the theories, which is why the drawing on the particular results or resources makes sense. And it makes no sense to postulate the whole new theory, a whole new theory on this particular occasion. We can even be quite tricky and use results or resources in a particular proof that deliberately and formally contradict what is said in another part of the proof, and do this without reasoning through the contradiction. To show that this is legitimate, we can use the strategy of chunk and permeate to ensure the soundness of the overall proof. Lastly, we might be using a paraconsistent logic to combine mutually inconsistent or formally contradictory concepts, entities, operations, and so on, or simply avoid using ex contradictione quod libet to prove a theorem we want to prove. Because of the richness of the conceptual resources provided by paraconsistent logics, more or less widely known by mathematicians, if they are worried, then they can avail themselves of these resources and be characteristically careful when mixing and matching from different theories. Otherwise, it is left to the philosopher concerned with the practice of working mathematicians to reconstruct the reasoning using paraconsistent conceptions to demonstrate the coherence or inconsistency tolerance in the practice of mathematics. All right, so any questions so far? Because I'm going to move to inconsistency in chemistry.
I just have a question. So, would you say then that there's an inconsistency between, for example, classical logic and modal logic? Because it seems to me that you will have to say that there's an inconsistency from the way you specify inconsistencies in your last slide. Since there seem to be some things that you can say about, for example, a proposition.
Right.
In the case of modal logic, that you cannot say
That you cannot
classical
say.
logic.
That's right. So right, I mean, at the meta level, right? So at the meta level, you can say, look, propositions are the sorts of things that might be possible or necessary. You can't say that if you're not allowed to use those modal terms.
Right. It's just.
So that's false if you're not allowed to use those modal terms.
I was just asking because it seems to be a peculiar use of the notion of inconsistency between theories.
Yeah, let's discuss it a little bit later, because you're right, it's a bit broad, and I might be misexpressing it. Okay. So inconsistencies in chemistry. Let's move on to chemistry. In contrast to mathematics, theories in chemistry are not so precisely individuated. It follows that inconsistencies in chemistry are not always formally blatant or clear. We might have a theory of carbons or a theory of electrochemistry. One is based on a particular set of materials or elements, the other on the types of reaction in subatomic or submolecular reactions in subatomic or submolecular theories. Inconsistencies might appear within a theory, between theories, or between general metaphysical conceptions. So they might even appear at the sort of metaphysical level. In the past, inconsistencies in chemistries have spurred research and have sometimes led to ideas being abandoned or, in theory, revision. Often what we find in chemistry is a pluralist attitude towards inconsistencies, or what is also called consistency tolerance. I quite like this term, inconsistency tolerance. We might hold two mutually contradictory theories as hypotheses rather than belief states, so we had this discussion yesterday, and defer deciding between them until such time as it becomes important, or until such time as we can think of an experiment that will determine which of the two theories is supported by the observation in the new experiment. Of course, in chemistry, theory determination rarely happens so simply, partly because of the vagueness of individuated theories. So the discipline might institutionally talk about different theories, but they're not delineated quite as precisely as they are in mathematics. I'm new to the area of philosophy of chemistry, and so cannot claim to have a thorough sense of the literature. However, and even if it's a small literature, I still don't have a thorough grasp of it. However, what I have observed in the philosophers of chemistry that I have read is that inconsistency is, one, sort of deflected by calling on so-called pragmatism, and that's an easy tick. Or two, it's deflected by calling on the notion of metaphor or ambiguity. Or three, by softening the appearance of inconsistency, by being quite sophisticated and taking seriously the language in which we express inconsistency, together with replacing the mode or fact or absolute truth of the relevant pronouncements in chemistry with more hypothetical or conditional modes in language. This is what Chang does, and I think what Salucci will be doing in a forthcoming book. Or four, softening the appearance by being careful about the representation in language, formal or informal, but retaining a mathematically classical, inconsistency, intolerant reconstruction of the theories and their relationship to each other. For example, Hetema uses the mathematical and conceptual apparatus of classical structuralism, and to some extent we can see this in the project of the, well, this is in physics really, of the Hungarians Andreka et al., who use classical model theory. Or five, by resorting to the strategy of chunk and permeate to cordon off notions in chemistry in such a way as to always escape explicit inconsistency, and that's a forthcoming work that we're working on at present. None of these philosophical attempts at addressing inconsistency in chemistry really entertains the idea that the chemical world might simply be inconsistent, or that our representation of the chemical world through theory and language might be inescapably inconsistent. It is this bold proposal that I should like to entertain here, as a conceptual exercise. So what is this bold proposal? So this is 3.1, consistencies in chemistry. Chemicals and their reactions might themselves be inconsistent. You haven't thrown me out of the room yet. or, this is maybe a little bit easier, our representation of the chemical world through theory and language, be it formal or informal, might be inescapably inconsistent. The disjunction looks a bit Kantian, and it's meant to. The first disjunct is very difficult for Western people to cope with, but let me just say this. If, in virtue of the construction of our formal representation, we foreclose on the paraconsistent possibility of inconsistent behavior in the entities or substances we study, then we foreclose a priori on the possibility of recognizing such if they come up. And the foreclosing speaks against the supposed open-mindedness of scientists, counterbalanced by rigor of argument that is always wholly present when reasoning, certainly paraconsistently. And this is important because this foreclosing is exactly what many scientists have done in the case of, say, quantum physics, and the theory would take a new turn if we were open to the possibility. Some quantum theorists are close to understanding this. So, for example, I went to a nice talk by Samson Abramsky in Helsinki, where he is well aware of the paradox and inconsistency in quantum theory. He draws a very nice distinction in the reasoning between what he calls local consistency and global inconsistency. So for him, the whole theory is inconsistent, but pockets of reasoning are each consistent. Moreover, he has a topological, logical meta-analysis of when it is that one is approaching the inconsistency. So when you're going through a proof, he even knows when you're getting close to that inconsistency. So the recognition of inconsistency is alive and well. However, his next reaction is interesting. He urges us not to go through the inconsistency. That is, we reason short of the inconsistency. This is quite sensible in terms of methodology. Of course, try to avoid inconsistency in the first instance, since it is difficult for us to reason through the inconsistency and hold on to the impression that we still understand. It's difficult for us. In other words, the phenomenology of such reasoning is unappealing to some people. And that is not to rule it out, that's not enough to rule it out in advance. The reasoning is not appealing to some people trained in, in contrast, the reasoning is not unappealing to some people trained in, say, paraconsistent reasoning directly and formally, or to people who have studied under certain schools of Buddhism. Personally, I think that it is a matter of time before paraconsistent reasoning is accepted, or at least experimented with, in quantum theory. I think that eventually there will be something Abramsky and his fellow scientists will not be able to reason through without going through the contradiction. But it's right to try to avoid doing that if you can. This should not be too alarming, moreover. After all, it's not as though the contradictory phenomena in quantum mechanics are completely chaotic and unpredictable. It is not the case that we have a trivial or logically explosive particle or wave. The choices of behavior are actually very limited. There are parameters around the behavior. It is just that we do not know in a particular instance whether the phenomenon will be like this or like that. Moreover, once we open up to this possibility, we might find that grosser chemical reactions between substances, compounds, or relatively pure samples of elements are also inconsistent, or are reasoned over better, where better is a matter of taste, training, inconsistency, tolerance, and so on, with a logical language that allows inconsistency but not explosion. We would then be better able to observe inconsistencies in reactions in chemistry, for example. And by this, I mean that we would be able to observe the inconsistency in itself and as a real phenomenon and as part of reality. So enough said about being inconsistent in the first jumped, right, of my bold statement. That was, no, where was the bold statement? I can't remember. Anyway, doesn't matter. Right. Since in a paraconsistent sense of possible, it is possible for objects or waves or phenomena to be inconsistent, then as good scientists, we should not foreclose on this possibility by constraining our language or inference rules. For the second disjunct, whoops, am I in the right place? Sorry, I should have had that before. Okay, so this is the second disjunct at the top. Now for the second disjunct. This is a lot easier for Westerners to understand. What does this amount to? We represent chemicals and their reactions using theories. The theories are written in a language or several languages, often a mixture of formal and informal language. Since we are discussing at the level of language now, we keep our definition of inconsistency from mathematics, namely it is the same as contradiction. Contradictions are expressed and recognized in a language. They rarely have strict we rarely have strict identity in chemistry. Right? So Needham makes this point in a paper in 2015. Rather, we have equivalence up to our purposes, sensitivities, equipment that can measure things, and relevance of context. So any contradiction might be in the language and theory, but not in the reality as such, right? It's not in the phenomena. It's just in our way of measuring it or some limitation. Doesn't follow that the representation, that is the theory in the language, should be changed. It might not be a bad idea ab initio to try to fix the representation. Check for vagueness, ambiguity, contextual differences, etc. But it might not be a bad idea later, possibly sooner, to not worry too much about the inconsistencies. In fact, this is what we observe in the practice. Different degrees of tolerance towards inconsistencies. In the practice, to be intolerant in principle, a priori, would beg the question. And as good open-minded scientists, we cannot decide in advance that our reasoning has to be consistent in contradistinction to rigorous, right? It does have to be rigorous. Here, rigorous just means prone to recognizable error and subject to agreed correction. And I might have to be more precise about that, I'm not sure. For example, we regularly reason over margins of unpredictability when we reason about stochastic processes, right, statistical things. When we do this, we might apologize and say that the stochastic talk is a patch, the best we can do, since the world is a priori, deterministic, causally linear, and inconsistent phenomena are impossible. In other words, we might attribute inconsistency to our representations without compromising our metaphysical convictions about the consistency of so-called reality. The inconsistent representation is hostage to the inevitable or temporary gap between the metaphysically consistency of reality and our inconsistent representation. And there are many places to look to improve the representation. Look to vagueness, look to the ceteris paribus clauses that sit behind our representations in language. But we cannot rule out in advance that inconsistent representation is intolerable. In fact, it is exactly this that leads to our refinements in our theories. So the inconsistency is fruitful in exactly this respect. It's temporary for most scientists, and that urges us to continue our science. It's when we find a problem that we develop science, not when there's no problem. There's no problem, we just carry on, we do our engineering or something. Moreover, practicing inconsistency tolerance earlier rather than later might lead to more fruitful discoveries in our science. Formal representation and even representation in the natural language hides aspects of reality. Descriptions are always incomplete. On the one hand, this is their strength. We cut out what is irrelevant in our reasoning or interests. But then the representations are inconsistent and there's no logical explosion. This is a nice call to become more explicit and to re-examine the ceteris paribus clause in our represented inconsistency. We might even be so bold as to acknowledge this at the logical level in our reasoning or in our language in chemistry and take the paraconsistent pluralist route to understanding in chemistry. Who knows? We might even go so far as to accept that reality itself might be inconsistent, but that might take a longer time. Conclusion. Am I okay for time?
Yeah, no problem.
Oh, good. Okay.
Well, we are late, but
Okay.
you are not.
All right, so, well, we're like collectively. It's a collective agreement. All right, so anyway, it's not too long, the conclusion. Having discussed inconsistency in mathematics and inconsistency in chemistry separately, I now ask the question whether one set of reactions by mathematicians or chemists can inform the other's practice and theory development. I shall be restricting my investigations to works of myself and Byers for the account of inconsistency and pluralism in mathematics, and to Chang, Schumer, and Byers for the account of inconsistency and pluralism in chemistry, just because I don't know the literature well enough to survey more than that. The first two of the mathematician strategies are rarely adopted by chemists but are available. However, the drawback for the chemist is that they depend on being able to individuate theories and chemistries in a very precise way. It is difficult to do this and to be loyal to the practice at the same time. Arguably, the flexibility in theory boundary and in representation are necessary for the advancement of chemistry. I do not advise the chemist to adopt either of these strategies, but maybe he or she will be well served to adopt the third, the paraconsistent pluralist strategy. This would give a flexible but transparent rigor to the reasoning in chemistry. The other way around, right? From how inconsistencies are handled in chemistry to how they could be handled in mathematics is, for me, a little bit more interesting. First, so I don't believe that mathematics has to inform chemistry and not the other way around. I think chemistry can inform mathematics too. First, in the practice of chemistry, as opposed to the philosophy of chemistry, there is an ignoring of the classical logical consequences of inconsistency. This suggests to mathematicians that they might relax their doxastic fixation on consistency. This ignoring, without further ado, is not available to the mathematicians, not without further ado. Right? Instead, second, inconsistencies in chemistry are the source of disagreement in the community and also the source of innovation. Moreover, as Chang argues, keeping conflicting metaphysical conceptions around and alive for longer, what he calls pluralism in chemistry, leads to more fruitfulness in chemistry, not less. How you measure quantity of fruitfulness is a fraught issue also, right? But this is one of his arguments. Thus, on the part of Chang, Schumer, and Byers, there is a deliberate recognition of the important role of inconsistency in the science of chemistry. Byers argues that this is also the case in mathematics, but he reports that mathematicians are reluctant to acknowledge this. Maybe mathematicians could learn from the example of chemistry, but take the issue further and be more precise and feed this back to the chemists. So there could be a very nice interaction between the two. Interestingly, when there is a disagreement in chemistry, this takes a political and institutional turn. But for the discipline as a whole, to God's eye view of chemistry, it is better to keep the inconsistency alive, maintain the tension, and encourage new concepts. Thus, with inconsistency, we have local or individual discomfort, but from the point of view of the discipline, a flourishing. This point is eloquently made by Byers in the case of both mathematics and science. So, last sentence. If we were to acknowledge it in mathematics, we might be better served to adopt paraconsistent reasoning at the at least meta-meta level, as I'm doing now, if not at the meta level or at the object level of our reasoning in mathematics and chemistry. That's all. Thank you.
Thanks for the talk. Of course, I'm sympathetic with a lot of the points.
But
Well, I'm trying to say something.
Of course.
Right at the beginning, when you're talking about individuating mathematical theories, it wasn't clear to me how you can draw those distinctions, right? Because if you go back, for example, I think it's one of your first slides.
It's the first slide, yeah.
Yeah. So you think about the first one, right? You can individuate in terms of axioms,
Right. Yeah.
Now,
Not every theory is axiomatically presented.
that's right. But think in terms of individuating in terms of certain principles.
Yeah.
So don't think that it's an axiomatic one,
Right.
which I think it's far broader.
Right. Right.
In that case, then that's just the way you do for group theory and ring theory.
Right.
Okay, so these are the principles, right?
Mhm.
And in doing that, of course, often you're introducing some operations,
Yes.
which is the third one, right? And
Right. These don't preclude each other.
yeah, but then I'm not sure what the distinctions are.
It was just, I mean, it's a bit loose, right? So
Okay.
it could, I don't want tidying it up. But it's just, if you ask a mathematician, so what is group theory about? They might give very different answers. Right? So they might say it's about the operations of multiply and together with a zero element or something like that. Or they might say, look, a group is a restricted sort of field. Right? So mathematicians might, in the practice, give very different answers.
And they will, but they are equivalent. So there's a sense in which.
Right, they're equivalent depending on the meta theory that you adopt in order to see that equivalence, and they're equivalent in certain respects. And of course, because it's the same thing, I mean, group theory is group theory, right? So your first lesson in group theory, right, when you first enter the class, they say group theory is about blah, blah, blah.
Mhm.
That first lesson might be different in different universities or under different professors. So,
Right,
so
but
there's-
does it matter?
that's right.
Is there any sense in which that difference is
Yeah.
significant? Right, because of course,
Because in the discourse, when you have disagreements, right, you say, oh, these two different theories are in conflict with each other. You might not recognize, say that, I don't know, say you're fixated on ontology or something. So it's different things that are looked at by mathematicians. And these things are sort of what bios would call proto concepts, like the number 8, right? And then you say, well, we can look at the number 8 from the point of view of the integers, from the point of view of the whole numbers, from the point of view of real numbers, and so on and so forth. And it's the same number 8. Now, somebody who's presented the same theories set theoretically might not recognize it at all in the same way.
Well, that's
So in other words, the disagreement will sound the discussion that takes place will sound very different.
right, but then either there is indeed a difference, or there's no fact of the matter, or the practice doesn't settle, right? So because I think
Practice doesn't settle.
yeah, because I think these contexts are different. One thing is group theory, the other thing is the number 8,
Right.
right? Because I think there would be far less disagreement
Right.
about, oh, is this group theory or not?
Mhm.
Then
Right,
is this
Right, is it
number
the
8
same
real
number?
number?
Right, that's right. And that depends on how you can see the numbers, the so-called
That's
number
right,
8.
yeah.
And what you think, whether you think that that's an ontological entity, or whether you think it's just the thing that happens to fill this space in this structure,
Mhm.
right? And that's it. So again, whether you see these presentations as being equivalent is going to depend a bit on what meta perspective you take.
Mhm.
So if we say we're disagreeing about the properties of the number 8, then how that discussion plays out will be sensitive to how we're individuating theories. Now, at the end, we might end up agreeing, right? And you might say, oh, we have to converge at the end every single time. I'm not sure we have to
Mhm.
either.
Well, I think it would, maybe this is just a different way of saying the same thing, right? That you depend on what your background theories is, right?
Right,
So,
right. Oh, yeah, exactly.
right, thanks.
Yeah.
I wanted to go back to this point where you said that we could recognize inconsistency in the world, because I'm not sure how that could look like. I mean, let's say we see white swans and then we recognize the black swan. Now, we only assume that there is an inconsistency if we assume that swans are necessarily white. But this is a moment where we change our concept and we say, obviously, we weren't using the term correctly.
Right, so that's not a good example.
Yeah, so, but my point is that any example I can think of, we would rather think we were not referring to the world correctly rather than think that something is inconsistent in the world. So I can't think of an example.
No, I know, it's really hard. So it's very hard, especially for Western people, right? Trained in Western ways to think this way. But if you'll allow me a little bit of slack. So think about the electrolysis of water. So you put a little electrode in some water and you have to convince me to get me right. So you have two little pillars there with air in them, and one of them fills up with hydrogen, the other one with oxygen. They're not connected to each other. The Phlogiston theory, so this comes from the Chang book, the Phlogiston theorist will see this as the water is being phlogisticated and dephlogisticated by the electrical impulse, the water, and that's what they observe. So the metaphysics informs their observation. What they see is water being phlogisticated and dephlogisticated. What the compound Lavoisierian sees is that the compound of molecules are being separated through the ions. So they see, so how we see something is informed by our metaphysical conceptions, by our theories. And then you see reality, if you can hold both of those at the same time, then you're seeing a contradictory.
In that sense, but then we are at the level of representations.
Well, I just did it. It wasn't that clever.
No, I mean, then we have inconsistency in our representations of what we observe. Because phlogistic chemistry.
Right, at the end, that's right.
Representations.
That's right. So the inconsistency is in the reality, and our representations are at fault. Right? So there might not be a fact of the matter either way, because we don't know which theory is the better one, which representation is the better one.
Okay, but that is still not.
So yeah, and I might have to.
I think consistent between these two conceptions. Yeah.
Let's put it this way. If you really, really want to hold on to the idea that reality cannot be observed to be inconsistent, you can hold on to it.
No, I'm not saying that.
Right.
But as soon as you use observed,
I know.
We are already in the level of representations. So I'm just saying, I don't know what it means to say reality is inconsistent, because as soon as we say what we see, then we speak of representation, and then we find.
Okay, good.
So,
that's
but
nice
maybe
one.
this is just the way how we use the term consistency.
Right. No. That's very good. That's very good. So let me see if I can think of a better example.
But we can also leave this for later.
All right. Well, I mean, take maybe quantum mechanics, right? So in quantum mechanics, there are going to be things that, I don't know, they just seem to be inconsistent with each other, right? And the reality seems to be, in some sense, if you're open to that idea. Now, if you foreclose on that idea, then you're not going to observe it.
Could you give an example?
Well, the electron goes through a slit, and it's either going to I don't know, through the interferometer, and it's either going to take this path or it's going to take that path. I don't know which one. All of these.
But doesn't that rely, for example, on not taking into account the collapse rule?
Okay, good. Right.
Part of the standard.
So again, you can see this in one of two. You can hold on to one of two things. You can say reality has got to be consistent. It's not possible to observe an inconsistency in reality a priori. Then you can always give an explanation that sort of forces a consistency on the reality and says our representation is at fault, if you want to. But you don't have to do this. You can reverse it if you want. Now, can you make sense of that? Well, that's really hard for us.
But all the examples you can give always use a language when we are wrote.
That's right.
So But
So
does
then
that mean that reality is inconsistent, or does it mean that our description of reality is
it
inconsistent?
means that either the reality is inconsistent or our language is inconsistent. We don't know.
No, our description of reality.
Yeah.
But-
So either the description is inconsistent or the reality is inconsistent. I don't know.
But what? No, take one disjunct.
Yeah,
Okay, reality is inconsistent.
but I don't know which one it is.
But what would that mean? Is there a
It's-
fact that
that's
at the
right,
same
that's right.
time
Look-
is not a fact, or is there? What does it mean?
The point is that I find it difficult to understand what that means.
Oh, you don't understand it either.
I'm not sure I do, no.
Okay.
So I find it really hard, but I don't want to foreclose on ever being able to understand that. I don't want to say a priori it's not possible, because I want to say that part of that is hostage to my training, I've been trained to see, brought up as a little scientist.
Practice, I'm thinking of Graham's example of Sophie's box.
Okay.
You encounter this thing, you've got this practice in your language at least of making observations, and they're observations of a kind you can ordinarily make quite straightforwardly,
Right.
consistently,
Right.
and you're quite happy with the practice.
Right.
And you look in the box and you find yourself reporting, it's empty, and there's something in it.
There's something, yes. Yeah, so there are going to be, but then
It's
if,
a fictional.
It's not very convincing, but I mean,
That's right, that's
That's
right.
a form of the kind of.
that's right. And what I don't want to do is to say it's a priori impossible for us ever in science to come across such a thing, unless what we did is we foreclosed on that metaphysically beforehand.
And then the question is, what cost would there be in saying, no, we're just never gonna swallow that?
I think the main problem is
If you
the
want.
notion of inconsistency, that the way how we understand it, how we've been using it, it refers it's something at the propositional level, at the level we
That's right.
apply to propositions.
That's
So
right.
I think what Didier was asking is, I don't know what it means that we say something else but propositions is inconsistent. So what means that the reality
Okay,
is-
so
Can I-
so then you go, one set of examples would come from the Buddhist literature. Okay, so they think of an object, identity conditions are not the same for them. So like a person is sort of a spread out entity. It's not a Minkowski worm in a Minkowski space. It's sort of a diffuse thing that, so whether it's consistent or inconsistent almost doesn't matter, So once you start to put on those sorts of hats and think in those sorts of ways, then you quite happily see the world as inconsistent. It's not and so-called reality is perfectly part of noticing that reality is inconsistent is a way of being more advanced in one's understanding. Whether that can ever play something in science, that's a separate question, right? Because science has been so driven by the West and so on and so forth. But I don't want to foreclose on science changing in that way.
Yeah, on the other hand, so many people have claimed that reality is inconsistent, and so apparently this education is not so deep, because people like that,
Maybe
but
you're right.
many
yeah,
others
that's
as
true,
well.
that's
It's
true.
just me that doesn't understand it, and
Yeah.
media perhaps.
Okay.
Yeah.
That's true. Yeah. So.
Certainly does.
Well, yes. I don't see what use of
But
this.
I could imagine that you say, I want to leave the possibility that,
Science
but
might
then you
take
need
that.
to refer to
It's a huge jump, right? And it would take, this is not something that will happen tomorrow in science or something. It's something that might happen a very long time from now. And I personally find a lot of difficulty with the idea too. I search for examples. But maybe with, say, vague objects or vague terms, so you've got a substance that's, you think fairly clear, fairly pure, and it reacts one way at one point and reacts another way at another point, and you think the context is exactly the same. Right? But it's reacting this way this day, and it reacts another way on another day, and it's not because it's Tuesday versus Wednesday that it's acting differently, right? That can't be right. or you're using different instruments, but they seem to be exactly the same sort of instrument. You're at the same altitude, you're in the same pressure, etc., etc.
You're making the same observation on an object in the same state.
Right, right. So again, how we interpret that, and it is really. I mean, I personally can't do it, but I don't want to say that it's impossible just because I can't do it. You know, those are my limitations, not the limitations of possible thinking.
Just thinking about this issue about whether we can understand what it means for reality to be inconsistent. My problem is I mean, if we can understand what it is for something to have some property or for something to be the case, and it seems like in those cases and in every case in which we have some description of reality, we have to use some vehicle for expressing that description, right? So it's not as if we could take a vacation from language and just understand what these things mean without propositions. So if in the standard cases...
Well, that depends on your notion of understanding, but yes.
But okay, so grant me just a certain notion of understanding. But, so the question seems to be that, to me, if in ordinary cases we can say, okay, you understand what it means for some object to have some property. And of course, we can say this in cases where I say, well, this is a black gadget or whatever. But in ordinary scientific cases where we're talking about space-time having some property or the universe having some symmetry characteristic or something like that, where we're not talking about inconsistencies, and no one claims that we don't understand what that means, then why is it specifically a problem to claim that we don't understand what it would be for the world to be inconsistent? I mean, it's just because just very quickly, just to sum up my problem is, so okay, you can say, okay, but these are just theories, right? These are higher level theories that in these theories we're saying that the objects have such and such properties or structures or whatever. But if there's some sense in which we can say that we understand what it means to say that, then perhaps there could be a case where, for some reasons of expediency or predictive success or whatever, it could be make sense to say that of some object in the domain that it has and doesn't have some property, or that something isn't the case. So.
Moses, you wanted to continue this thing. For me, inconsistency is clearly always related to negation.
Okay.
All the examples Michèle gave, like A is different from A, that's because A equals A is also a theorem of logic, otherwise there would be no problem. The same with 0 equals 1. So what is, if I understand what is a negation in reality, I will be happy, but I don't.
Right, good.
But
Good. Yeah, that's right, because we have to express, and this is Dunya's point too, is that we, at the end of the day, we have to express that inconsistency in language using negation.
That's okay.
Sense. Yeah, I'll think about this. It's a very nice quote. I'll push myself on it harder.
Yeah. And another small question, your very last sentence of your text, not of the slides. Kind of, well, I have always difficulty to follow a read lecture, okay? This is not your problem, it's my problem.
No.
But it kind of, I'm not sure I understand.
Okay.
Because you wanted to, it's related to the discussion with Ottavio, of course.
Yeah, I nearly crossed it out, actually. So if we were able to acknowledge in mathematics, let's see. Thus, with inconsistency, we have local and individual discomfort, but from the point of view of the discipline of flourishing, if we were able to acknowledge this in mathematics, we might be better served to adopt higher consistent reasoning at the meta level or the object level or the meta level in our reasoning in mathematics and chemistry, or about mathematics and chemistry.
And this is a point I've heard you make several times, but I'm not sure I understand it. What is the use of having this meta-meta level consistent?
Well, if I'm discussing two theories that in the language in which those theories is expressed, one says A and the other one says not A, then at that meta level, I'm going to have to be able to deal with that. If I want to say that they're not, that inconsistency is not trivial.
Yeah, but the fact that the color of the color of Christian's hair is different from Moses' hair does not. I can say this without being inconsistent. So if I'm talking about two theories, I say this theory, that.
No, that's right. No, that's not inconsistency, right? But objects in one theory, I might want to think, are the same objects in the other theory. So Moses' hair is dark and Moses' hair is light in one theory, but it's dark in another theory. If I want to make sense of that, electrons should collapse towards the nucleus, or electrons should stay orbiting.
But I mean something extremely simple. I always do. We have competing theories and they contradict each other.
Right.
Is there any problem saying this theory claims that and that theory claims that?
No.
Can't we do that in a consistent way?
Yeah, we might be able to.
Of course, if you want to amalgamate the theories, then you will need by consistency.
Right, or if you want to say, look, there are some properties of the number 8 that are shared in the two theories.
Yeah.
When we talk about the number 8, we might want to hold on to that linguistic convention. And when we do that, then we're going to sound as though we're talking about inconsistencies, or we're speaking inconsistently. And it's not a problem. I mean, in the practice, it's not a problem. When we speak normally, it's not much of a problem. But so what look like contradictions, just because of the language that we're using, they're not problematic contradictions. Does that help?
Follow up. Maybe this example can help. Imagine that we have an empirical domain that call it B, and B is divided in B1 and B2. So you have a theory that explains satisfactorily B1, and another theory using A, and another theory that explains satisfactorily B2, but it depends on using the negation of A, or for B's.
Yeah, but these are two theories contradicting each other. I have no problem with that. And if you want to talk about both theories together, so this is the case.
It seems that you say that, so there is no problem because you interpret A under the light of a particular theory, and you interpret the negation of A in the light of another theory, and then you have consistency in a higher level. No?
But Maria, I think there is no problem to describe the situation if you just want to say this theory explains that and the other theory explains something else. There's no problem to say that consistently.
Right,
which is
what you did.
But the explanation of the bigger domain of B requires you to conjoin those theories if you want to make a bigger.
But I admit if you want to amalgamate the theories, or if you want to say I want to create a new theory out of them, of course, then yes, you need by consistent viewpoint, whatever you're over, whichever mechanism. That's no problem.
Okay. Yeah, that's much better.
Just my last question. So it seems that one thing that keeps coming up during the discussion is you mentioned the notion of proto concept, and it seems that there's also the notion of inconsistency that you're using. Overall, in your talk is a sort of proto concept, because, for example, you point out, okay, these are different senses of inconsistency. For example, this language is impoverished with respect to that language, and when you take this theory and this theory, they you get an object that has a property and doesn't have it, etc., etc. And all of those incompatibilities seem to be different in many respects.
Right.
But and later you say, okay, but
right.
perhaps you could solve this in many ways. For example, you could say, okay, when you take this background theory, then maybe you can show that they are the same, or maybe you could show that they are compatible in practice, etc.
Right.
But just my point was that all of these strategies seem to be required whenever you make this posit, which in a sense is some sort of metaphysical posit, that there is some notion, some proto-notion of inconsistency, which is workable even before giving some formal language or theory in which you can talk about inconsistency, right? Because you earlier said, I have this suspicion that when we're talking about the number 8 in this context and in this other context, it's the same object. And perhaps, perhaps there are some cases where that is true, where the intuition we have about some object actually is the case, and in whichever theory we try to work out, that's the case. But perhaps as a general notion, this notion of inconsistency, where some proto concept we have must always behave nicely in this way, so that we can say it has identity conditions. Maybe that we cannot cash that out always. So that's a concern I have. Perhaps do you have? I don't know.
Yeah, what I said about the proto concept was a little bit in brackets, right? It was in quotation marks. So if I'm following a certain train of thought, the notion of a proto notion of inconsistency I haven't thought of yet. So I have to think about it. But yeah, press me on this in the next months. Yeah, good.
So I think we're running out of time, so I would suggest we thank the speaker.
A brief pause now.
Yes, 10 minutes break.
10 minutes.